Okay. Yep. So that's based on several joint works, which are related to studying the Jordan order property, but the results are from different preprints. So here is the list of the co-authors, which is long. So my plan is to motivate the subject, like why we are interested in studying relative homology and what are the topics that are related to it. And then I will define the categories we work on. Then we'll give some examples and some consequences of having this nice property on certain categories, like what does it give us a data. So first, let me mention the people who worked on this before. There are origins of defining the extension functors, which required having enough projective or injective on a category so that we'd be able to build these homology functors. But you need to have an idea to how we could define this functor on a category without needing having this projective and injective. So the way is to map the image to some short exact sequences that we can construct on any additive category. And so that in this way, we can define this functor on a general category. And then we can study property relatively to reducing this functor by taking additive sub-bifunctor of this functor. And several people studied this before, for example, studying the derived functors or etc. And there are also some recent works by Oslander and Solberg, and they were trying to apply this idea to representation theory, studying relative co-tilting models, for example, Artin algebra, etc. So the idea is that we want to take, let's say, an additive category, which has nice properties of morphism that form a vector space. And then we want to take class of short exact sequences, and we want to study property relatively to a choice of the short exact sequence. So we don't look at the exact category here as like embedded, and it's a category embedded in a model category using a functor, like embedded in an abelian category, but in a different way, like in a more explicit way, by choosing a class of monomorphism and epimorphism that behaves well. So that's the idea, because there are different ways to look at an exact category on an additive category. And let me first motivate the general why we are interested in studying, like why we want to get out of the abelian case. Like, let's say abelian category, like model category over a finite dimensional algebra, or abelian groups, they're nice categories that behaves well and have nice property. So why we would like to take a more general setting, like, for example, taking an additive category, not necessarily abelian, and choosing an exact structure, which is in the case that I want to discuss today, is a class of short exact sequences that satisfy some properties. So monomorphism and epimorphism that are kernel-kernel pair that behaves well, because in different settings, it's more flexible and give us more flexibility. Like, for example, in homological algebra, these satisfy lots of nice property, like one can generalize what it's already generalized, like all the homological lemma, like Snake's lemma, Nine lemma, etc. all works well in these settings. And in different settings, they give us more flexibility and freedom to do things, like, for example, in functional analysis, etc. So our motivation came first from wanting to generalize the Gabriel-Reuter measure, which is a measure used to prove Brouwer-Thrall conjecture, some conjecture. And to do so, we needed some length function. And so that will start our motivation. And then to define this length function, we needed Jordan order property. And so to study which category satisfied this property, we needed to define intersection, sum, radical, etc., which are nice objects that behaves well in general in the abelian case. So we needed to study these notions in the exact case. And while studying these notions, we get some characterization of some additive categories. And we could also relate it, since other people were working on the subject, we could also relate it to Grothendieck group. So these were our motivations from a specific topic, studying the Jordan order property. But there are also other people who use the categories that we defined to prove other results, like the unique decomposition in abelian category, which is a result due to Hanini-Krause. They generalize it to the exact setting. And there are also so some of these results work in a more general setting, like for extrapolated category, which is something that we recently did, but it's more technical, so I won't go in details in the extrapolated case, but just to mention that what I'm talking about today is exact case, but also some of these results can be studied in the extrapolated, which is a more general setting that generalize exact and triangulated at the same time. So it generalizes the exact categories, which is additive categories with an exact structure that behaves well to inherit the characteristic of an abelian category, like abelian groups, etc. And at the same time, triangulated category, like derived category, for example, etc. So we are further studying this property in a more general setting. Some more motivations that are more general is that relative homology showed that it can solve some problems. Like, for example, in persistent homology, they're interested by some invariants. Persistent homology is where they study how some property persists, and it's a main tool of topological data analysis. And in this setting, some invariants were recently defined using the relative homology, using the relative Grothendieck group of an exact category. And there are some recent works by the group in Sherbrooke, but there are also Lewis, who is a postdoc also at Northeastern, who also have a recent work on this. And I guess he can say more on the role of exact structure in relative and relative homology in persistent homology. So yeah, it's in defining some invariants, and the goal will be to prove they're stable, etc. But that can also motivate why one can be interested in relative homology and in changing the exact structure. Okay, so yeah, I guess that enough of motivation, that you're now motivated to see the definition. So an exact category is a pair. So we choose an additive category, and with an additive category on it, we choose a class of short exact sequences. So we fix, as I said, the additive category A, and now what is the exact structure? So it's pair of kernel co-kernel morphism. So E is a I is a monomorphism, and D is a epimorphism that we can compose. So they are kernel co-kernel pair, and so we have E. Then we should compose it with some T, and so the composition will be 0, but it's not just a weak kernel co-kernel, it's a kernel co-kernel pair. It's closed under isomorphism, under direct sums, but the direct sums are consequences of the axiom. And so it's not any class of kernel co-kernel pair that could be called an exact structure. It should satisfy some property, like, for example, that the identity should be a monomorphism, an admissible monomorphism and admissible epimorphism at the same time. So identity, these are two dual axioms. Also the composition of, so the first one is the two first dual axioms. Identity is mono and epi. The second one is the two other dual axioms. The composition of two admissible monic should be an admissible monic. And the pullback along any morphism of an admissible monic should be, the push out along an admissible monic should be an admissible monic, and the pullback of an admissible epic, if we take any other morphism, should be again an admissible epic. So these are 6 axioms, but they are like splitted into dual one. So 3 on the monomorphism and 3 on the epimorphism. And so if we take a category in general and a different category, the existence of this kind of structure on it depends on the property of short exact sequences or property of monomorphism and monomorphism and epimorphism on the category. And so it depends on what this category has as property will allow us to find out which exact structure can be defined on it. And the opposite is true. Sometimes the existence of a structure on a category can tell us a lot on what is this category. For example, is it weakly idempotent complete? Is it pre-abelian? So pre-abelian is a category that has all kernel and co-kernel. Is it, for example, semi-abelian, like, for example, the category of groups? Like abelian groups is abelian, but just groups is semi-abelian. Is it quasi-abelian, etc. So here we go from a particular case, which is a very good one, to the more general case. Okay, so let me discuss some examples. So first, what is a quasi-abelian category? It's a pre-abelian category that has all kernel and co-kernel, but also all kernel and co-kernel are semi-stable. And by semi-stable, we mean that if we take the push out along a kernel, it gives again a kernel, and a co-kernel is semi-stable if the pullback on it give again a co-kernel. And so we can talk about stable short exact sequences, and we will see where these define an exact structure. So if we take a quasi-abelian category, then the stable short exact sequences, for example, will form an exact structure, not just on quasi-abelian. Even if we take weakly idempotent complete, they will satisfy the axioms and form an exact structure. But yeah, in the quasi-abelian case, it's all the stables are all of the, by definition, are all of the short exact sequence. And so it's the biggest one. So any other exact structure is in it. And that's an order that we can define. So we can, on any fixed additive category, we can order the structure by inclusion, just a class. So that one would be the biggest one, for example. It's also the same, the stable also is the biggest one on the weakly idempotent complete category. So it's just in the quasi-abelian case, it's all of the short exact sequence. So that's one example. Yeah, another example also I can mention is so as I said, they're ordered. So any structure will be in the maximal one, which is all of them and all of the stable in the quasi-abelian case. But also we have a minimal one, which is formed by all the split short exact sequence, like the retractions and sections. So if you take section retractions, these short exact sequences exist on any additive category. These form the minimal one. They always form an exact structure, and it's always included in any other structure. So this is the minimum. And here I just want to mention as a remark that as we order them by inclusion, so if we take the poset of all structure on a fixed category, we order it by inclusion. We take the intersections and some joint, but it's not really the subject now. But we can order the set and we can prove that it's a lattice. And also if you see, one can see also an exact structure as additives closed subbipuncture of the extension function. And so seen in this way, they form a lattice, but also seen as a class of closed additive subbipuncture, they also form a lattice. So there is an isomorphism between these two lattices. So I just want to mention here that we have usually different choices of exact structure that we can choose. And so it makes sense to study what happens if you reduce the structure, for example. But there are some rare cases, of course, when we have just one structure. Because, for example, if you take a triangulated category, the minimal and the maximal one will be the same one, will be just the split one. So the only structure that exists is the split one. So yeah, sometimes we only have one, but usually they're different and we have different ones. So we always exist, at least they exist one, and we usually have different choices. So that's the point. But I won't go in detail of the combinatorial structure of lattices here, since I decided to talk about that in the combinatorial seminar Monday. So yeah, I will not go into these details. So one thing that we decided to study is the Jordan order property on a category because we wanted a good length function. So anyone can define, we try like the length function by just taking the maximum of sequences, but it doesn't give a nice function, just give a function. So we want a nice one, like that satisfies properties that are similar to the abelian. So let me first remind you what's this property in an abelian category. Like let's say, for example, abelian groups or models. So if you take a model over a finite dimensional algebra, then any two composition series like these inclusions are monomorphism, injections. So if we take inclusions, if we take two different composition series of the same object, then in this case, they will be equal, and the composition factors, like the quotients between successive one, will be the same up to permutation. And so this is the theorem in the abelian case, which allow us to define a length function, because this length here will be the same, so an equal m, which give us a number, and so we can define using this number a well-defined length function. This is how the length function is defined on abelian groups or models. We have this unique number, so we can define a length. But in general, if you take any exact structure, which is supposed to behave well, it's not always the case that we get one unique number, and so that we can take it to define a length. So what we decide to do is to study when this will be satisfied. So instead of taking in an abelian category, like you can keep in mind abelian groups or models over an algebra, we have, let's say, sub-objects or monomorphism or an injection here. Instead of that, we will take an admissible monomorphism, which means that a monomorphism in the exact structure. For example, if you take the split one, this will be a section. If you take the maximal one in the abelian category, there will be any inclusion, etc. And instead of taking simple sub-object, this time we'll take admissible simples, which mean that there are no admissible sub-objects, just the zero one. And so using these two, instead of talking about composition series, we can talk about admissible composition series and study the property. And then we will need to have some notions of intersection and sum. We'll see this later. However, not every property that is satisfied on the abelian case will behave well in the exact case. For example, the admissible sub-object of a fixed object form a lattice in the abelian case, but they don't really form a lattice in the exact case. So not everything stays the same. Okay, so this is here what we will call an admissible composition series. So we take a filtration by sub-objects, but not any sub-objects, like they should be related by only admissible monics. For example, if you take the minimal one, which always exists, like the split one, these should be all sections. Yeah, etc. And we take quotients as E, semi-simple, like the cokernel. The cokernel of every morphism of these should be admissible simple. And so if the category has a unique length of this composition series, then we call it Jordan order. And since now I will show you that in a very simple example, there are examples and counterexamples, so it's not always satisfied. And that's why we were interested in investigating more. So if we take the category of representation over the A3 quiver, so which means we take for every vertex vector space and for every arrow linear map, and so we get representation of this quiver. This category have 3 almost split sequences, which are not split. And so these ones with the ending are indecomposables, etc. will, well, in this case, they will generate, under some conditions, these sequences, almost split sequences, generate all exact structure. So each time we choose one of these, we generate an exact structure. So if we choose, we can keep in mind, like I call them 1, 2, 3. So if we choose 1, it generates this exact structure. If we choose the 2, this one. If we choose a subset of 1, 2, it generates an exact structure. If we choose the...
On the first slide,
yep.
You have, so I is the injective, P is the predictive, and
yes.
S is
the simples.
Simple. Oh,
so the S, it will be like, for example, S1 will be K0, 0, for example. So 1, 0, 0. So it's the simple one.
Okay,
and same as 2, put like it would be 0, 1, 0. And so S2 will be 0, 1, 0, and S3 will be 0, 0, 1. Yeah. And so 1, 2, 3. So each time we take one of these. Oops, the slides are not moving. Okay. I don't know.
That's all right. Projectors are like the ones that follow the arrow.
Yeah, like the one you take one, well, which one would project on? Let me just reshare just because they are frozen. Okay, reshare. Don't know why it's frozen. Okay, let me just check if it's frozen everywhere. Oh, what's wrong? Yeah, like the question. I like it though. I think it will work. Just give it a few seconds. Okay, it's working again. Let me share the screen here. Share screen. That one. Okay. Oh, it's frozen again. No. Okay, good. So we're back. So like if we choose, for example, 1, 2, 3, then we get the maximal one. And the minimal one is always the split one, section subtraction. So here we get like 2 power 3, which is 8 exact structure, because we have 3 here, so 2 power 3. So here are the exact structures. Now they also here form a lattice, like a Boolean one, if we order them. So we have the minimal one at the bottom and the top, and it's complete and bounded. But yeah, that's not the subject. Now let's say I take the exact category formed by this additive category, which is abelian, and this exact structure. This one is not Jordan order, because we can take for the same object 2 different composition series with 2 different quotients. Like the quotients are different here, as we just see from the short exact sequences here, we have got 2 different quotients. So this one is not, and that one is not. So here we have 2 that are not. The rest are Jordan order, like the maximal one is the abelian one. Every abelian category of models or representation is abelian, so it's Jordan order. The minimal one is always. So here we have these 2 that does not satisfy, because we have 2 composition series of filtration on the same objects that filter in different ways, because the quotients are different here, the co-kernel of these 2 admissible monic. So here we have 2 admissible monic. And these are different. The quotient here is different from the quotient here. And so we can see that even if we take an abelian category, we can get counterexamples. So the things we were looking for, then when is this satisfied? And one of the way of studying this is by considering intersections and sums of subobjects. And so that was our approach. So if we take an object, a fixed object, we want to study the intersection of any 2 subobjects in it, or the sum of any 2 subobjects in it. And so let's say we take an exact category and we call, so yeah, the first intuition was like just taking the abelian intersection, like the pullback, and let's hope it works like for an exact category. So we take the pullback. So we take this object here and we take the pullback of 2 admissible monic, of these 2 admissible monic, and let's say this define the intersection of these 2. So, okay, let me repeat. So I have C, an object. I took this admissible subobject and this admissible subobject, and I want to define the intersection of these 2, so of A and B. So I can take this as the pullback. So let's hope that this worked. That was the point, by taking the pullback. And by taking the push out on the pullback, which is would give us U, which is given by the universal property, and that one would be since it's the push out on an admissible monic, will be by the axioms and admissible monic. So let's take this as the sum. That was the point. And so the idea is if I came back here, so here is a pullback on an admissible monic. By the axioms, we know that the push out on admissible monic is an admissible monic, but not the pullback on an admissible monic. So we need to add this extra property on the category to make this intersection admissible, because we don't care here about just only subobject, like by inclusion, we care about admissible subobject. So I care about P being admissible, or the intersection, the pullback being admissible in the object C. That's what we want. So we ask for this extra property. Let's say we call this an extra axiom, and this one an extra axiom for the sum. And does this, so when we have admissible sum and admissible intersection, then that ordinal property will behave well. But yeah, sorry, what did I say? Okay, yeah, and here we take both of them. So we say, because we want admissible intersection and admissible sum, both of them, to get the property. But what happened is that not just the quasi-abelian category has this property of admissible intersection is only true on the quasi-abelian. So we just get that it's true if and only if the category is quasi-abelian, which is a nice characterization of a quasi-abelian category, but it means also that that won't be true in the general case. We also on the way get a characterization of the abelian category, that if we want admissible intersection and sum, in this sense, taking pullback and push out, then the category has to be abelian. And there are also more characterization of an abelian category. For example, it's abelian, as I said, if it has admissible intersection at sum in this sense of pullback and push out, but also if we take an admissible morphism. So let's call a morphism admissible if and only if it factors through an epimorphism and then a monomorphism. We call this an admissible morphism. So if we want all the morphism to be admissible on a category, then this only happens when the category is abelian. Same thing, if we want to be able to compose and add, like to compose in the normal way and add this morphism, admissible morphism, so that they form in a vector space, for example, this is only, so if you want the sum of two admissible to be again admissible, let's say, or composition, this is again only true in the abelian case. So this is again, all of these properties are only true in the abelian case, but we know we can factor through the image in the abelian case. So in the more general sense, this is only true in the abelian category. If you talk about factorization with using admissibles, like for example, I don't know, of any exact structure, like the split or the stable or etc. Yeah, so since this is only true in the abelian and quasi-abelian, now it's nice. We know that this happened only on the abelian, but we want it in a more general setting. So we want to define an intersection that works on any exact category. So we first consider the pose set of admissible subobjects. So as I said, it's not necessarily a lattice in the exact case, but we take all of the admissible subobjects of a fixed object. So it depends on what's the structure. If we take the split one, for example, it will be the direct summand. If we take a fixed object X, so X here, we want to consider all the subobjects of it, using an admissible morphism. And I said it's a pose set, it's a totally ordered set by the inclusion. And if we define this, sorry, not an inclusion, this order, and we define this order using if we can factor it that way. So in this way, it's a partially ordered set. So we have an order on it. So we take all the admissible subobject of a fixed object X. So here X is the fixed object, take all its admissible subobject. And we can order them using this order, which is not a totally order, and which is not a total order. Yeah, okay. So now I consider for two subobjects of a fixed object X, because you keep in mind that what we want to define is the intersection of two subobjects in an object and the sum in an object X. So we consider here A and B in X, and I take all the Y's which are admissible subobject of A and admissible subobject of B at the same time, so which are in common. and I take the maximum of these things in common. And that's what generalized in some way, or it's a construction that we want it to be the intersection. So it will be the set of these. And here it's not necessarily unique, just the set of all the objects that will be the maximum. And yeah, we will see an example on this. And so if you have intersection, I can define a radical in the same way, well, in the similar way of the abelian case. I can take, so S here is the same things as P, the poset. I just don't consider 0 and X. That's it. And for the sum, we take, so again, I have X and I have A and B in X. And so I take all the Y's that are in X that are admissible subobject, but that contain at the same time both A and B. So like I want the ones that, so I have Y. So I want A to be in Y and B to be in Y. And now I take all these Y's that are in X that has A and B, both of them. And so if I take the minimum of these, then I have the same problem. I think doesn't like the black pen. Yeah, I will share it again. So each time I use this black pen, it's tall. Okay, I will share it again. Sorry. I think it doesn't like this pen. So we were at the sum, intersection at sum. I think I'll stop using the black pen. Yeah. Yeah, okay. So let me share it again. Share screen. Okay. Okay, so what I was saying here is that, oh, that's not the one I want to share. Sorry. I should open this in the, okay. Can you see it now? Okay, good. Why can I draw on it? Okay. It's not the one I want. Oh. Okay. Okay. Okay, great. So yep, we were talking about the intersection and sum. So we take all the ones that have an A and B at the same time, the admissible subobject that has an A and B, and we take the minimum of them. So this is the sum. Like the intersection is the maximum intersection, like this is the minimum of these objects that have A and B at the same time. And let me show you an example which make the idea more clear. So if I take an additive category as the category of all vector spaces that have even dimensions, so we don't want the old one. And since it's an additive category, it's guaranteed that we have at least this exact structure, the minimum one, the split one, the section and fractions. And if I take this as my exact category, and I take X as, so I want an object in this category, it should have even dimension, right? So I take K6, which has dimension 6. So this object works, is in the category. And let's say these are the generators. And I take these two sub-vector spaces, and they're also both. So you see, I take V1, V2, V3, V4, and then I change in the second one, but both had dimension 4, which is even. And now we want in this exact category to find the new intersection, like we just defined, and the sum. So here, oh, I see that you can see everything. Okay. So the intersection, the abelian intersection, like if I just take the intersection we know, we take the one in common, which is 2, 3, and 4. So this is like the one that just we used to take, but that one is not even, it's of dimension 3. So if we want to take the admissible intersection here now, it will be all the vector spaces of dimension 2, which are in this vector space of dimension 3 here. So we take all the one of dimension 2 here. in this one. And so that won't be a unique intersection as the abelian one. This is more general. So we have a set. Here we have the Grassmannian, which is an infinite one. So we have plenty here of subobjects in it. And that's what we mean by this intersection. It's not anymore a unique one because we don't have any more a lattice of subobjects. Yeah, and the sum will be here just X. But yeah, that's to compare like this intersection we used to the new intersection. And so using this intersection, we can consider some nice categories that satisfy that all these three properties are equivalent. That every short exact sequence is in this form split if and only if X is semi-simple, which means like would be a sum of admissible simples, like the simples we just defined, admissible that doesn't have any other admissible subobject. We take so semi-simple mean here just that there are some of it, and that the radical is 0. So if these three are equivalent, then we consider this category called Artin-Wedenburg. And there may be a better way to define this category, like finding some condition that is simpler than saying that these three are equivalent, but I don't know it yet. Yeah, and so if the exact structure on a category satisfy these, then we will call it an Artin-Wedenburg exact category. And why we were interested in these categories, because so if you take the minimal one, it works. It satisfies this property, like the section retraction, which is not surprising since these section retractions behaves well. But also, and if you take a Krull-Schmidt category, which is Hom-finite and idempotent complete, which means that every idempotent morphism, so idempotent complete means that every idempotent that we compose and give will have a kernel and co-kernel. So if you take Hom-finite like that, then we can prove that this kind of categories satisfy the Jordan-Alder proof. That's why we're interested in this technical category, because they give us nice property of that filtrations will have the same length, so that we can have a length function, etc. But also, so here we just know one sense. So is the opposite true? Like every Jordan-Alder should be a category like this? And we were able to prove that if and only if for some categories, for the Nakayama, the models over a Nakayama algebra. So let me first recall what is a Nakayama. So first, a model is uniserial if this set of subobjects, when we take all short exact sequences, is a totally ordered set that we can order any two subobjects. So there would be only like one filtration. Yeah. And a finite dimensional algebra is Nakayama if every indecomposable left and right projective is uniserial in that way. And so for this nice algebra, if you take the category of models over it, then a category will be Jordan-Alder if and only if precisely when it's Artin-Wedenburg, the one we were interested in, like the equivalence, the one that satisfies the three condition equivalence. So this is a characterization in this case. Yeah, so that's it. I won't say that in general one sense work, and if and only if works in this case for this special category. Okay, yeah, and now why we want these categories that have this nice property of Jordan-Alder, because as I said, we were able to define a function, a length function, by taking just the maximum length of any filtration, like taking X, and since we have different filtration of different length in general, we can take the maximum one and define a length. But this length won't satisfy all the properties as the length of abelian. But this time, if you take the Jordan-Alder length, which is given by the length of a composition series, then now it will behave better. Yeah, so that's how we will define the length, by being n, the length of an object will be the length of an composition series, like the co-kernels will be E-simples, etc. And we were able to compare the two lengths, but here I just will talk about the nicer one, the nicer length. And so this gives us a function. So we take an isomorphism class of an object and we can give it a number if it's finite. So here we're just studying the finite ones. We're also studying the infinite ones, but it's not, I'm not ready yet to talk about the infinite. So what it satisfies is that if you take any admissible short exact sequences, then the length of the one in the middle is the sum of the other two. And we have only one inequality if the category isn't Jordan-Alder, if we take just the maximum as the length. but if we have the equality if the category is Jordan. So this is a better property. And also, yeah, and that one also works for the general length, but also works here. So if we fix the exact structure and reduce it, then for a fixed object, the length will be reduced, since we will have less admissible monics. So when we reduce the exact structure, the length will get reduced. Good. And yeah, and here that result in fact works for any category, for any exact category. So if you take an Artinian and E-Noetherian object, which means that, so Artinian and Noetherians mean that when you filter with the sub-object, there is a bound, like there's somewhere where we can stop. And if it has both, it stops when we filter by both sense, then we can prove that it has a composition series, that there exists one composition. So this sense is true, like always. But for the opposite, it's not always true, but it's true if we take the Jordan order category. So this is here, this condition here is necessary to have the Jordan order because it doesn't work otherwise. So if we have it, then E-Artinian and Noetherian will have a composition theory, but also having a composition theory will be Artinian and Noetherian, which means that we can talk about an object would be E-finite if and only if it has both properties. So, and by E-finite, I mean it have a finite length. So like there's a finite composition theory, which gives us a finite length. Yeah. Oh, yeah, that's it. Okay, I haven't put more. So I'll stop here. Thank you very much. Maybe I finished earlier. Yeah, I don't know how much time is left, but it's fine. Oh, fast.
Any questions? Oh.
Hi. Hey, I think I might have a question.
Yeah, sure.
One of the things I was curious about is like, do you for like these exact structures, like, do you have a sense of when there's enough? You can define the notion of, I guess, projectives and things like that.
Yeah, relative projective.
Yeah.
Like by taking instead of epimorphism, admissible epimorphism, then you get a relative projective. So
yeah, so if you start with a category of modules or whatever, but you take one of these like exotic, I don't know, exact structures, or like these non. Do they always have enough projectives?
I don't think so.
Okay. Is there any like?
Do they always
understand?
Have, do they always have enough projectives? Well, in general, okay, no, because in general for the abelian case, it's not always true, and the abelian is a special case, so we already have counterexample in the abelian.
Right. But if you start with a category of modules so where the abelian one definitely does have, well, okay, yeah. If you start with a category of modules where the abelian one does have enough projectives.
Then do the others have enough? I don't know.
Yeah.
But I don't know in this special case.
Okay.
But in general, it's not always true. But that's a good question. I don't know.
Yeah, I was curious.
Yeah, I'm not sure. That's a good question.
Okay. Yeah, I was just trying to understand what these other exact structures kind of mean, but cool.
They could be like many different things, like stable, strict, well, any closed by functor of the extension functor. Like by closed, I mean exact in the middle. Like if there is exactness in the middle of a sequence, then the image by the functor will be again exact, then it will be closed. Any subfunctor like that of x1 will be an exact structure, like it's isomorphic.
Thanks. Yeah.
Thank you.
Any other questions?
Anyone here has questions? But you don't have to if you don't have any, it's okay.
So what about the Solberg, Ausener-Solberg, sub-bifunctors of X, right? So how do they give you exact structures like that?
Yep. They give exact structure.
Particularly nice ones, right?
Yes, they give exact structure. We thought at the beginning that they may be weakly exact structure, like by missing the composition axiom, but we're pretty sure now that they give exact structure, which is better, which is a nicer property.
Okay, yeah, I think we can look at those.
Yeah, that one are very interesting. These two articles are long, but they're interesting.
Okay.
Eva, would you? I thought you were asking a question.
Well, maybe just the definition of AW condition that you have these three things being equivalent. Is there like another, you mentioned that maybe there's another way to?
Yeah, that's the thing. So I believe there is a better way, but I haven't found it. So it is, if these three are equivalent, then this is the category we're interested in. But that's like not the simplest way, I guess, to define it. I'm pretty like, I believe that there would be a simpler condition that implies these three, but haven't yet found it.
I see.
Yeah.
But for the case of the Nakayama algebra model.
For the Nakayama, these are equivalent to Jordan model. Yeah. Yeah, but I mean, in the general case, maybe there is like a way to describe it, which is more general than Jordan model. Because it's if and only if just in the Nakayama. Yeah. But I mean, in general, there would be a condition that can imply these three, instead of like writing this a three.
Interesting way to phrase it. Yeah.
Yeah. Well, I need to think more about that.
Okay, very cool. Okay, thanks.
Thank you.
All right, if there's no other questions, let's thank Souheila again.
Thank you very much. Thank you.